So in some ways, it's new material I'm putting into this course, but I think it's fun. All right, so here are 4 binary strings of length n, right? In some really, really, really big number. Here's our 4 binary strings, all right? And my question is, we're going to keep, this is a repeated question. I'm going to keep asking this question. Which of these strings is more random, right? And so my first kind of answer to the question, which is more random, is going to be to know how they were produced, all right? So how did I get this first string? Well, you'll notice it has a pattern. It goes 1 0 1 0 1 0 1 0 1 0, right? It has a pattern to it. The second string here, the way I got it is I asked Google what pi was, and it said it was 3.14 right? And then I asked Google to convert that into binary. And this is the binary representation of pi. You'll note it starts with 1 1, which is 3, right? 2 plus 1 is 3, right? So that's what pi is. This one down here, the way I generated it is for each bit, I flip a fair coin, right? And how did I generate this one? Well, I flipped the coin for each bit, but it wasn't completely fair, right? In fact, I'll tell you a property of the string here is that the number of zeros is slightly less than half, right? In a random string that was really, really, really long, you would expect that the number of zeros was pretty close to half, right? And this one, it's the number of zeros is going to be exactly equal to 0.49n. All right, everybody got how we got these 4 strings?
Sir, what do you mean fair coin, unfair coin?
Oh, a fair coin is that when you flip it, the probability it gets heads is 50%, right? And an unfair coin is, it's slightly more likely to get a heads than a tail.
All right, yeah.
Right?
Yeah.
The probability of a tail was 0.49, and the probability of a head was 0.51, right? So it was a biased coin, right? Does that make sense? Right? If you are playing dice with the gang down in your block, they might kill you if they figured out that you were playing with unfair dice, right? All right, so now we can ask which one is more random, and what do you feel about it? Is the first one random? No. This one here, it's the definition of random, right? I produced it by flipping coins. And this one's almost random, but not quite random. This one's definitely not random. It has a pattern. What about this one? Is it random?
Yes.
We could say there's no pattern to it. So we could say it was random, right? We could say that, right? Certainly, if I told you the first billion bits, you would have a hard time telling me what the next bit was, right? All right, so let's ask the question again. Which one's more random? But this time, let's say if I were to flip a coin n times, what's the probability that I get this string, right? What's the probability I get this string or this string or this string, right? Anybody know? Right? Well, the first time to get this string, there's a 50% chance that I get a heads the first time, and then 50 that I get a tail, then 50% I get a head, and 50% I get a tail, right? So that's 2 times 2. It's right. The probability I get this, exactly this string, is 1/2 to the n. Right? Everybody agree with that? And that's the same for all of these strings, right? They're all equally likely if I were to flip coins. So we might argue that they're all equally random, right? They all have the same probability. You could say, oh, well, what's the probability of getting this string? Well, it's pretty small, but the probability of getting this string is equally small, right? They're exactly the same. Right? Everybody get that? All right, so let's ask another question. Again, which one's more random? And we can ask which one has a short description, right? So if you're going to just describe it to me in English, which one has a short description, right? So this first one, I just say, hey, it alternates between 0 and 1s. I guess I got to tell you how long it is. I guess I have to tell you that it starts with a 1, right? The second one has a very short description, right? It's called pi. Maybe I have to say pi in binary, right? But it's still a short description. This guy here, how could I describe it? If I needed to tell you the string, right? How would I describe it, right? Well, you could be smart aleck to me if you wanted, and you could say, well, this exact string, I'm going to call it Bob's string. So now it has a short description, right? That's Bob's string. All right. Somehow it feels like cheating, but let's come back to that, right? Now, here I'm going to ask, how many descriptions are there of length with n-1 bits, right? Let's just count. Let's say a description is, right, it's basically a binary string, right? If this is an ASCII string, and I convert that string into binary, right? So basically I'm describing this binary string with this binary string, right? And so I could ask, how many descriptions are there that are only n-1 bits long, right? Well, how many how many strings of 0s and 1s are there that have n-1 bits? That's many of them, right? 2 to the n-1. Everybody know that, right? Because there's 2 choices for the first bit and the second bit and the third bit, right? That's how many descriptions there are that have this length, right? So what can we say? How many binary strings of length n are there? There are 2 to the n of them, right? There are 2 to the n strings like this. So what can we conclude here? We conclude that half of these strings need at least n bits, right? If I chose this string randomly, then with probability a half, it's going to need at least n bits to describe it, right? So to say that this one is called Bob's string is a bit of a cheat, right? Another way of thinking about this is a communication complexity, right? Suppose Bob flipped all these infinite number of coins and Bob knew this string and he needed to send me bits to tell me what the string is. And we could have any communication method whatsoever, right? In order for him to tell me in random bits, he really does need to send me the bits, right? He has to send me in bits to tell me in bits. That's just a law of communication complexity, right? Does that make sense? Right? So we can say which one's more random. We can say based on, right? So back here, I guess, this one's not so random because it has a finite description, right? And this one's random because it seems to need an infinite description, right? Now, this whole idea of a description, what's a valid description and what's not, right? People could get worked up about, well, what language? Are we doing this in English? Are we doing it in Chinese? Are we doing it in ASCII? How are we interpreting these descriptions, right? Who told you that this symbol was pi, right? It relies on some previous knowledge. And we want to get away from that idea, right? So in order to get away from this, I'm going to ask a new question about which one's more random. I'm going to say, which one can be outputted by a Java program with a short description, all right? So the way we're going to get these strings is you're going to give me a Java program that has a shortest description possible. And that Java program, we're going to run it on no input. You just run it without an input, and it's going to start spewing out digits, right? It's going to start spewing out bits. And because the string is infinitely long, right, we will never, oh no, actually it's only of length n. Sorry, if it was infinitely long, it would never stop. So, but it could spew out all the bits. But our string is of length n, so it eventually will spew out bits and eventually stop, right? And we're going to say, we're going to describe the complexity of the string as the length of the shortest Java program that outputs it, right? And that's called Kormog complexity. This guy was some Russian, all right? That's why he has a name that sounds like that, all right? Does that make sense? People get this definition here? All right. So again, we can say the same thing. How many computer programs, how many Java programs can be described by n-1 bits, right? Well, only 2 to the n-1 of them, right? Because there are only 2 to the n-1 strings with n-1 bits, right? So what does that tell us? That, well, they're 2 to the n of these strings, and so half of these strings require programs whose length is whose the Java program is at least length n, right? Does that make sense? Are people kind of following this? Right?
Yes, sir.
Right. So here, look at here's the Java program that's outputting this, right? It's pretty short. Here Newton could give you a Java program that could output all the bits of pi, right? Here, these were all flipped randomly, right? When I flipped them randomly, you could do a little math here to prove this. What's the probability I get a string that can be described with n-k bits, right? You can always describe a string with n bits, right? You just say print, and then you give me the string, right? So it's slightly more than n bits because you have to count the word print, right? So every string can be written with n+5 bits by just saying print the string, right? But can it be described by n-k bits? You know, is there a Java program with n-k bits that can output it? And the probability that happens, right, is exponentially close to 1, right? That it needs at least this many bits, right? So almost for sure, you're going to need all full n, almost n bits, right? Now, here we flipped an unfair coin, right? And we could ask, so this is what I was, I was up canoeing and I was asking the question, right? How big of a Java program do I need to output the string, right? And so that's what we're going to talk about now. Is we're going to focus on writing a Java program that will output the string. And here, let me first tell you something about it. Right, this is a string that has the property that the number of zeros is exactly 0.49 n, right? So I could ask how many strings have this many zeros? And the answer is, right, I rounded things a bit, but more or less it's this is the number of such strings, right? Here, this number is, right? So you'll see what you should know about 0.99997 is that it's slightly less than 1, right? Because the number of binary strings is 2 to the n, 2 to the 1 times n, right? And this is slightly less, right? Now, you might ask, where did I get this number from? And we won't go into the math of why this is the case, but let me tell you how I computed this number, right? This function h is called the entropy function. Shannon's entropy, which we could learn more about entropy. It's a great subject. But basically, h takes in a number between 0 and 1, and it does this calculation. And if you put in 0.49, it comes out with this number. So that's how I got from this number to this number. All right. And so now what I'm going to prove to you is that there is a computer program that has this many bits in it, that's described by this many bits, and it outputs any one of these, right? For any string with this property, I can give you a Java program that only has this many bits, and it outputs your favorite string, right? And that kind of tells me that these strings aren't quite random, right? Because they have shorter descriptions, right? Instead of the description, most strings need descriptions of length n, right? But this one requires description that's slightly smaller, right? Does that make sense? This particular string is less random because it can be described by a small Java program, right? Usually we think about randomness as a distribution, but here we're going to talk about it. It's sort of random because it has a short description. All right, so which one is more random? Well, these are very patterned because they have very short Java programs. And this one's completely random. And this one, hello, mother, I'm trying to hang up on you. There, I just hung up on my mother. And this one is not quite so random, right? Because it has a shorter description, right? Does that make sense? Is everybody following this? All right. Now, let's just point out that we're not caring about running time here at all, right? We're just all we care about is, does it output the right string, and what's the length of its description, right? And let me tell you, I have to hang up on my mother again. What are we saying? So why am I teaching you this? Well, one, I think it's cool, and two, computer science is all about describing things, right? Having descriptions. So I do think it's kind of relevant to computer science, right? All we're talking about is the information. How much information is in the description of the Java program, and how we translate that over to the information of the string that we're outputting. All right. So how does this relate to entropy? Suppose you took your room and you cut your room built in half, right? So there's this half of the room and that half of the room. Mother, hey mom, you really got to stop calling me. I'm in the middle of a class. This is my room, and suppose you counted the number of particles, and there were slightly fewer particles on one side than the other, right? Then this wouldn't be considered random, right? We would say that the entropy was low, right? You know, one thing about so some guy came up with the definition of thermodynamics entropy, and they kind of argued that entropy always increases in the universe. And this is what he meant about it, is if you had the system, entropy of the system would increase. How is particles would fly back and forth, and then you would have the same number of particles on both sides, right? Everybody follow that? So now, how would thermodynamics define entropy? Well, they have a sense of a microstate and a macrostate, right? So the microstate tells me, it tells me the position of every, maybe it uses a binary string, right? The microstate uses some binary string to describe the position and velocity of every particle. All right. So that's the micro, right? You get right down to the little bits and you tell me the microstate. And what's the macrostate? Macrostate is you can just observe it. Maybe I'm observing the pressure on this side versus the pressure on this side. I'm observing that in a macro sense, there's a higher pressure on one side of the room than on the other side of the room, right? That's our macro state, right? And so our property is going to be there are more particles on one side than on the other side, right? And then thermodynamics entropy, what does it define entropy to be? Is you let in, given that your thing has its macro state, how many microstates are there equivalent to it? And you take the log of that to get the entropy, right? So that's thermodynamics entropy, right? And you see, you're taking the log of it. Is that because you're having a description? If you have capital N objects, then each of them can have a description of length log n. But the guy who came up with this definition didn't know about information. We had to wait for Shannon to talk about information. Anyway, then we also talked about commutative clause complexity of a string, right? Is the minimum number of bits to describe a Java program that outputs the string, right? So now we can talk about the Comarov complexity of a macro property, right? What's a macro property? Remember, is saying, hey, I have 0.51 in particles on this side, and I have 0.49 particles on this side. That's a property of the string. So the Comarov complexity of that property is if I gave you a string, what's the length of the shortest Java program that can identify, will tell you whether it has the property or not, right? So this is kind of tells you how complex the macro property is, and this tells you how complex the micro property is. Anyway, here's a theorem that I proved. I'm sure somebody proved it before, is that these definitions are all related, right? So these numbers are really small, right? So it doesn't take a big program to count the number of ones and see if it has exactly 0.49 in zeros. So these take small Java programs. And then that tells me my Comarov complexity is about the same as my thermodynamics definition, right? Right, and what's cool about this is that it tells you if your universe is in a low entropy state, then no matter what that state is, it's just one location of the particles, right? We can talk about one location of the particles, and we can talk about that it's in a low entropy state because I can describe the location of all the particles with the smaller Java program, right? You don't have to be thinking about the set of all possible states. You can talk about one state of where are my particles, and if I can describe that with a small Java program, then the entropy is low. All right. And maybe this has all gotten longer than I hoped it will, but we can finish in a couple more slides. All right. So our microstate, remember, is some binary string of length n. our macro property is that the number of zeros is exactly this, right? In capital N is the number of strings of length n that have this property, right? And so let's think about it. Let S sub Cn be the set of all binary strings of length n with exactly Cn zeros. All right. And so then we want to know how big is this set, right? It's the choose. If you might remember choose, right, is I have a string of length n. How many ways are there to choose where to put Cn of the bits, right? Because I want C of the n of the bits to be 0. So I have to choose those those Cn spots to put the zeros. And this is a bell curve you've seen before, right? Most of strings are 50-50, zeros and ones, right? And then you go over 1 standard deviation, 2 standard deviations, 3 standard deviations. The size of the set goes down really quickly. All right. So as I've sort of hinted before, one approximation of the size of the set uses this H function. Here's a plot of the H function, right? And you'll note that if C is a half, right? So here we're C and a half. So H of C is 1. And the number of strings 50-50 is pretty close to 2 to the 1n, right? Now, if C is 0.49, then we're shifting over slightly, and the number of such strings is smaller. And if C is 0, how many strings are there that have 0 zeros? Well, there's only one string of 0 that has 0 zeros. It's the string that has all ones, right? So that's why if C is 0 or C is 1, right, we get H of 0 and H of 1 are both 0. And that's because we're of this. Everybody kind of follow this? Anyway, we're focused on this right here. We have let S be the set of all strings that have exactly 0.49 in zeros in them, right? And that's how many there are. And the entropy of that is you take the log of this number, base 2, right? And the log of this base 2 is just that top bit, right? And you'll see that the number of these is right, the entropy is less than n. Are people good here? Are you following this? Yeah. Shanaz, you're back. Were you following it, but just camera off?
Yes, I was just having my tea, so.
Oh, well, we can watch you drink tea.
Okay, thanks.
All right, so here, now let's understand this a little bit better. What have I got that listed here? I've listed all binary strings with n bits that have exactly 0.49 n zeros. See, this one has this distance is 0.49 n, right? And I've listed all, and here over here we have 0.49 n zeros, and this is all strings of that have that property, right? That's my set S. And how many of them? There's this many of them, right? Over here, I'm going to put down what betas, which I called labels, right? And this is going to be all strings whose length is 0.9997 n, right? And here I just put them alphabetically, right? 0, 1, 2, 3, alphabetically, or ordered by cardinality, right? Here they are ordered, right? And how many of them are there's the same number, right? So that gives me a mapping from these strings to these strings, right? Does that make sense? So each string here kind of has a smaller description, right? So this string is of length n, but it has a description that's slightly shorter, right? These strings aren't completely random because each of them has a shorter description, right? Does that make sense? Right? So this is a crazy mapping, right? It's a crazy mapping. Now I'm asking, can I write a Java program that will compute this mapping? It's going to take as input beta, and it's going to output the corresponding alpha. All right. So I'm going to write this Java program. All right. So because remember, we want to say that each of these strings here has a small Kolmogorov complexity, right? Meaning they have a short Java program. So I'm going to write a Java program that's going to output any one of these strings, and its length, the length of the Java program is going to require this length description. All right. So let's start with a Java program, which given alpha tells you whether or not it has the macro property, right? So what does that mean? You give me a string, any string alpha, it returns yes if the string is a binary string of the length n that has exactly 0.49 in zeros, right? Can you write the program like this, right? It just counts the number of zeros, counts the length, checks that it's all binary, it says yes, right? It has a very short description, right? Now, here's another Java program. You put as input one of these, the ith binary string in this list, and what it outputs is the ith plus first binary string in this list, right? It just gives you the next one. Anybody can think about how to write such a program? Here it is. Here's the code for it. I'm going to think now, these are binary strings, right? But remember I told you can think of a binary string as an integer. So I add 1 to it, right? I just take the binary string I have, I add 1 to it, and now I have a new string. And I ask, does that new string, oh, I guess there should be a sub I here. Oops. Does that new string have my property? And if it has the property, I return it. If it doesn't have the property, I go to the next binary string. And if it has the property, I return it, right? So I'm going through these strings, right? These strings are in order in terms of their integer value. So I keep going to the next integer, until I get one that has the right number of zeros, that has the property. Does that make sense? So it just gives me the next string. All right, so now here's a program which you give it beta and it outputs alpha. How does that one go? Well, it starts off with basically the 0 string, and then it keeps asking, it counts. It goes, give me the next string, give me the next string, give me the next string. Every time it gets the next string, it counts, and it counts at the beta. And when it counts to the beta one, it prints out the string, right? And so here it's counting these, and it will return that string, right? So this program, do everybody see how this program, here's a program, and it prints out our favorite string, right? Taking any string here, alpha, here's a program that outputs that string alpha, right? And the running time might be horrific, but we don't care, right? What we care about is how many bits does it take to describe this program? And how many bits? Well, it's the number of bits to describe this program. Well, first there's how many bits in this. Well, that's just maybe it takes 1,000 bits to describe that. And how many bits does it describe to take for this piece, well, that's pretty short code. We can get that into the the 1000. What about the code for this, right? That's the Kamar complexity of the property, right? And now what's remaining here? What haven't I counted in our description of this code? Anybody guess? It's the beta, right? How I have to get the beta into the program. And how many bits does the beta have, right? The beta is the thermodynamics. It's the definition of it's the log of the number of possible strings in S, right? And that completes our proof. And so what's the point here is that this thermodynamics measure of this one string somehow tells me how random the string is. And oh, this just says we can go the other direction. Oh, yeah, let's not worry about it. We're getting too weird here. That's it for that. Any other questions? So that took me a half an hour. Maybe it was way too much. Did people find, could you tell me, did you find that interesting? Did you find it useful? Did you find it boring?
It was interesting, but a lot of I would have to go look at it at the video again and kind of understand it, especially the thermodynamics part, the last part.
Right, right. And it's kind of teaching you a little bit of stuff outside of the scope of the course, but I think it's good to know about entropy and randomness, and it relates to lengths of descriptions, and there you have it.